Hi, so I am testing a different approach. This time I'm using a Zoom to to try and record this session. So we'll see how it works. So if you recall, in the last video, I collected data, and now I'm going to enter those data onto a score sheet and calculate the error. And well, we're going to predict a score and see how it compares with the actual scores we observed or collected. Um, and um, and then we're going to measure the error of our prediction. So the reason I wanted to try Zoom is because I would like to share my screen with you while I do this. And um, I believe this is the one I want. And so if you can see what I have here, I'm going to try to enter the scores that we collected. And And for starters, I want to tell you that we're just going to make the same prediction for every observation, and that is we're going to predict 0. So let me enter 0 here under our column for prediction for every observation, and we had 10 observations. Now I'm going to enter the actual score that we observed. What I have done is I've set up this spreadsheet. If you look over in column E here, you'll see I've done a column that we can call error. More precisely, it is our score y minus our predicted score, which is y with a cap over it. So this is the error. So if I predict 0 and I get 0, I have 0 error. If I predicted 0 and I had a score of 5, my error score would be 5 minus 0, or 5. So I'd have 5 error points. If I had predicted a -5, my error score would be -5 minus 0, which would be -5. And that would have been my error points. What'll happen after that, this column over here, F column, is the squared error. So once I take a value, I will then square that error value. And that'll give me this squared error for each observation. So if I'm off by a lot, by squaring it means I'm going to be off by a ton. If I'm off by just a little bit and I square it, it's not going to be a big source of error. So the scores that I got when I collected my data were: observation 1 was a score of 5, observation 2 was a 5, observation 3 was a 4, observation 4 is a score of 2, observation 5 is a score of 9, 6 scored 4, 7 scored 6, 8 scored 9, 9 scored 3, and 10 scored 6. So these are my real scores in this column, and I'll color it. Let's just color it light blue. My predicted score was 0 for everybody. So let's color that in a light green. And now I have my difference, which is 5 minus 0, 5 minus 0. So you can see that 5 minus 0 gives me an error score of 5 points. So you can see this guy here at scoring 9 was a large error, and this one at scoring a 2 was only a small error with this predicted model. Let me make that a yellow. And finally, I take each of these scores and square it. And so I'm going to put that in a light orange just to distinguish it. What you can see is that if I had a little error like 2, squaring it didn't make it a whole lot worse. If I had a huge error like 9, squaring it made it 81. So it really amplifies the mistakes by squaring errors. That's one kind of advantage of it. So now I have a squared error term, a squared error value for each participant. But what I'm interested in knowing is what is the error term, the sum of the squared errors. So I'm going to take this last column and I'm just going to add these values up to figure out what how much error I generated. So you can see that my sum of squared error for, I'll call it SSE for sum of squared error for a model predicting 0 for everyone, it gave me a score of 329. Now, can we do better by any chance if we do something different? If we use a different prediction? Let me send it out just so it's easier to see. Well, I had said that we kind of know from a deck of cards that if the range of scores is 1 to 10 and they're where we think in the population they're probably evenly distributed, it's a fair guess to say, well, maybe the average is 5.5. So let's replace our prediction of 0 with 5.5, okay? So I'm going to insert 5.5 in there. And now we can see what we get. Notice how this time we have some negative scores and we have some positive scores. Again, by squaring the error term, it makes it large. It makes everything positive. We don't have to deal with pesky negatives now. And we can add them up. And so notice now when we do a sum of squared error where we predict 5.5, now our value becomes 48.5. That's a big improvement if you think of it. What an improvement to go from 329 sum of squares down to 48.5. So that's nice. So we're thinking, yeah, I don't think 0 is a very good model. So in this case, we would say we would reject the model that predicts 0 in favor of a model that predicts 5.5. Let's try one more thing. I'd mentioned earlier that we would consider a model where we predict the average or the mean score. So now I'm going to get the mean for our data. And it looks like it's about 5.3. So I am going to, let's see if this will work. I'm going to pop in 5.3 for all of our observations here. That didn't work. So let's just do 5.3 and copy. Okay. And now these are our error terms. Again, we have some positive, some negative. We square them, and if you square a number less than 1, it becomes even smaller. So an error of 0.3 is pretty remarkably small, and it contributes very little error. But we have one big observation, this one outlier here that had error of 3.7. Well, we square 3.7, and that turns it into 13.69. So you can see that this person is kind of an outlier. That's score number 8. So given that, now we have our squared errors for each subject, for each participant. We can add these values up and we get a sum of squared error when we predict the mean, and that is 48.1. And there you have 3 models, 3 simple models, nothing fancy. No, we're not even using another variable yet to try and improve our prediction. We're simply using a constant in the first 2 cases, a constant of 0, then a constant of 5.5. And then in the third one, we're using, again, it's a constant, but it's a constant that's a parametric value. It's the average score for these. And you can see what happens to the error. You can see that the error reduces dramatically as we pick improved models. It turns out, of course, in this case, these 3 simple models, the best simple model is the one that predicts the mean. And so going forward, that's what we're going to adopt in almost every case. That's what we will adopt as our simplest model. And that's what we will compare every subsequent model we build. As our models get more complex, we'll be comparing them against a model that just predicts the mean, with the idea of seeing, have we improved upon that, basically predicting the mean. I will stop sharing at this point and I will end this conversation, and then I will look forward to chatting with you further. Thanks.